This session is going to cover subject titled the Scalable Fault-Tolerant HPC Supercomputers. What we plan to do is to have a 25 more or less minutes of presentations, which will cover some of the topics that we think are interested. And then the rest of the time we want to do it open discussions, and definitely questions and remarks, and what you think, and what we think, and try to make it as most interesting as possible. I'm Gilad Shainer, I'm Director of HPC at Mellanox. Steve Lyness, who will take and do the presentation, VP of HPC Solutions at Appro. David Race, Shannon, and Professor Boku from Tsukuba University will be the panel. We'll try to answer some of the questions. We'll put questions. And we'll definitely want to hear questions from you or your view of the subject. So with that, now it's your turn to be famous.
All right, thank you very much. So one of the big things that we see is we continue to grow out the supercomputers, right? As we go beyond just 128, 256, 512 nodes is an increase in the need for additional fault tolerance within the systems. Right, and that includes improved building blocks, improved scalability, power and cooling capabilities, a lot around software. Right? I mean, you can have different levels of hardware capabilities, but without the software to back it up to create the true fault tolerance, having redundant hardware is only of a certain amount of use. Right? And the ability to really provide a complete end-to-end package that's going to increase the reliability so that as you start to scale out these systems, they can continue to grow, but you're still able to get the jobs to run. Right? So when you talk about fault tolerance, there's a number of pain points. There are some that are pretty obvious, right? The ones that have the highest level of failures, right? So the hard drives, power supplies, and fan trays. The other ways to address fault tolerance within the cluster are going to be around the system level. So these are going to be fault tolerance at the management nodes, fault tolerance around the networks, right? Both the IPC high-speed networks as well as the management networks. And then on top of that, you've got the application level fault tolerance, right? So the ability to have an MPI that's going to have the capability to take advantage of multiple rails, for instance, or the ability to do checkpointing in a very realistic sense, right? Because one of the big problems now is the ability to do a checkpoint in a reasonable amount of time that you're not actually wasting so much time that the checkpoint becomes basically useless, right? You're wasting more time doing that than you would if the job failed. A lot of what needs to be done is done, and I use this as an example, is our xtreme-x architecture. Right? So if you look at the overall system, right, we start all the way at the top with the management nodes being completely active, redundant with an active-passive pair. You work your way down into sub-management nodes that are also in a redundant pair, right? Dual Ethernet, dual InfiniBand, all of those capabilities be tightly integrated into an overall solution. So as the HPC applications continue to evolve, right, as they continue to scale out, as data sets continue to get larger, right, the applications need to be able to scale to increasing number of nodes. Right? So now you've gone from a couple hundred cores, right, on the high end to multiple thousands of cores. Right? But as you do that, you're adding additional fault points within the system. And as you look at the overall MTBF of a node, as you add additional nodes, right, the ability to have a job run from start to conclusion, right, becomes a little bit more iffy as far as being able to have that job finish without any type of interruption. So InfiniBand has become a very big part of HPC clusters and fault tolerance. there's a lot of capabilities around InfiniBand that makes it an ideal interconnect for being able to run very large jobs in a fault-tolerant configuration. And we've got very high bandwidth, very low latency systems that allow you to, even in the event of a failure, continue to run at a reasonable rate despite a loss of a link, a single path. Right? The system can continue to function and get the job done until that particular piece has been replaced. The other thing is the addition of fault-tolerant topologies. Right? So there are certain topologies, whether it be a factory or a 3D torus, for instance, where you can really work around failures within the system if you have the appropriate level of management capability at the top and a building capability within the silicon, right, down at the hardware level, to be able to do things like adaptive routing. Right? So this is an instance of that Mellanox is able to do. Right? So this is talks about adaptive routing and the use for congestion control. Congestion control is obviously a big pain point in a lot of instances, particularly where you're running multiple applications within some of these larger clusters, right? Because you get competing requirements for bandwidth within a cluster, not only for IPC traffic, but as we continue to bring in all of the different I/O needs, right? So the storage, the IPC traffic, the management traffic. Right? As those converge into a single network, the need for adaptive routing continues to increase. As far as fault tolerance is concerned, right, you've got a similar requirement on the ability to work around problems within an InfiniBand network. Right? So whether that be through adaptive routing, where you're going to fail around a bad component, right? If it's a bad switch or a bad link within the system, or if you are doing something like multipathing. Right? So that's a very real possibility where you actually create a second path to fail over to in the event of a hardware failure within your system. The other part, as we talked about, is the ability to do some of the higher level, right? So having fault-tolerant management servers at the top, typically in an active-passive pair, right? Where that management server is managing your InfiniBand network, it's doing the provisioning of the compute nodes within the system. It's a very important part of having your cluster up and fully functional, right? So this is typically going to be your biggest pain point, right? Because you lose your management server, you lose the entire cluster. Then if you have multiple levels, right, to be able to really scale out, you start creating a second level of management that will manage smaller portions of the cluster so that you can easily re-provision. Right? But then you need to have redundancy also down here at the sub-management level. Right? And then if you want to go one step further, now you create a completely separate and independent InfiniBand network, right, commonly called dual rail, where you have a second option in an ideal situation. It's a load balanced option where you can actually utilize both links fully, balancing traffic. Right? Or you may decide that you want to segment traffic in a fully operational system. Right? You send your IPC traffic out over the green and your storage traffic out over the blue. You fail one of them, now the remaining fabric can take over and do all of the functions that the two had done until the first one gets repaired. Other ways to increase fault tolerance, right? So the first one is I think pretty obvious. You're going to try to reduce the number of components that can fail. So one of the ways is by doing diskless boots. So that way you're actually pushing the disk, the storage capability outside of the compute node, so that you're actually booting off of those management servers or some sort of a PXE server. Now you boot the node off of the management system, the compute node doesn't have the hard drives, which is the main failure point. Increasing adoption of the interconnect topologies. Right? So you can actually go from a fat tree to a 3D torus for a very large configuration. And one of the main advantages of that not only is going to be in cost, right? Because you're reducing the number of switch ports that will be required, but and cables. And reducing those two, especially around the cabling, is going to decrease the number of points that you're likely to have a failure. Right? And then sub-management nodes, right? And the ability to have systems that are able to take advantage of that scalability, right? And have the fault tolerance at that level. And as the systems continue to get faster, right, as we go through the next generation of processors, whether it's Intel's Nehalem to Westmere to Sandy Bridge, or AMD to going up to Magna cores, right, those systems become a lot faster, a lot more capability, so you can actually decrease the number of those sub-management nodes, because now they're able to actually run, manage, collect information from larger groups or subgroups within your cluster. Dynamic provisioning, right? So this is another way to be able to manage fault tolerance, right? So being able to have failure notification within your systems, validation of the systems as they go through their boot process. And so reconfiguration of the system becomes much faster. So as systems are brought up, health of the nodes as well as the infrastructure can be taken, and the systems can be rebooted or rerouted. The jobs can be moved before the problem is actually going to occur, right? Or is going to take down your entire job. And then file systems that are going to allow scaling, right? Because you actually take the libraries and now you move them up in the hierarchy so that you're able to take advantage of the high-speed bandwidth, right, and low latency of the system, and be able to make single changes, and that will affect the entire cluster. And then at the application level, right, you get fault tolerance out of the MPI layer. Right? So, for instance, Intel MPI is now beginning to provide true multi-rail support. Right? And this improves message throughput, improves reliability because it will be able to support the fault-tolerant dual rail capabilities that I was mentioning before. Right? So that if you can load balance with two rails in the event of failure of one, you're able to fail all of the traffic over to the remaining rail. Right? So that's a big pain point within some of these extremely large clusters. Right? And then MBAPICH 2 and OpenMPI have also begun to support similar fault-tolerant capabilities. So some of the parts that are not covered by MPI, the operating system obviously needs to be able to take more responsibility for reliability. It's a little more difficult to have that level without the operating system being able to take full responsibility at the node level. Right? I mean, you can fail nodes, you can fail networks, but you also need to have that capability down in the operating system.